Welcome to the second episode of Calculus Made Easy. Today we'll discuss what is derivative. As our boy Walter White says, it's change.
Goddamn right.
So in very simple words, derivative is the rate of change for very small changes. So usually while discussing change, we ask with respect to what? Our boy Newton says with respect to time, but Leibniz was onto something. Not everything might be related to time, so let's keep it with respect to x, a variable. In simple language, anything we want. So let's introduce some terms and symbols. What does an independent variable really mean? It is a variable which value does not depend upon anything. Usually we denote this by using x. Second is a dependent variable. Its value depends on the independent variable and is said to be the function of the independent variable, so it is denoted by f of x. Third, what does d mean? D means differentia, which means differentiate. What does the elongated s mean? It means summa, which means to sum. Let's get an expression for the derivative. Let h be small change in the independent variable. Since a function is a dependent variable, change in function will be defined as f of x plus h minus f of x, which will be our first equation. Then again, change in independent variable will be h, of course. So the rate of change of function with respect to the independent variable will be change in function by change in independent variable x, which will give us an expression f of x plus h minus f of x divided by h. Then since h is very small, so small that h is almost equal to del x is represented by dx and del fx will be represented by d f of x. Then we will get an expression which gives d f of x by dx is equal to limit as h tends to 0 of f of x plus h minus f of x by h, which is also called the first principle of derivative or the definition of derivatives. So why do we actually take the derivative? The number one property is it gives a slope. But why? Let's look at the graph and find out. Changes in the function as well as change in the independent variable, which gives us a triangle. Taking the ratio of the change in the function and the change in independent variable gives us tan theta, because a right angle triangle is formed here. So we know the slope represents the formula of the derivative and will continue to do so even if h tends to 0. You might have seen from the clip that the derivative also gives tangent. A tangent has many significance in mathematics as well as in physics. So now let's take a break and enjoy tangents of different functions at different points. Now I would like to tag Prakash Pant.
Let's explore some popular uses of derivatives. If you are in high school, you must have heard that you get a local maxima or local minima at a point if the derivative at that point is 0. But why? Look at this graph and a moving tangent. You can notice that at vertex of the parabola, tangent is parallel to x-axis. Thus, the slope of tangent at this point is 0. Now to explain why slope of tangent should be 0 at vertex of the parabola, notice that to the slightly left of vertex, the slope of the function is negative and so functional values are decreasing. But to the slightly right of vertex, the slope is positive and the functional values are increasing, which is why while going from left to right, there must be a point where slope is 0 and functional value is no longer decreasing. Thus, that is the minimum point or vertex or local minima, whatever you say. Now let's look at concavity. If a part of curve opens upward, the part is concave up. If a part of curve opens downward, the part is concave down. The definition is simple. Now let's look at further mathematical elaborations. Notice that in a concave up parabola as shown, while going from left to right, firstly there is a negative slope which gradually increases and becomes zero in vertex and gradually increases even more. Here, since the slope is increasing throughout the interval, derivative of slope, that is second derivative, is also positive throughout the interval. So we can say a concave up graph will have positive second derivative. Similar is the argument for the fact that concave down graph will have negative second derivative. There's finally an interesting application of derivatives in evaluating limits, L'Hopital's rule. Let f of x and g of x be two functions such that f of c by g of c goes to 0 by 0 form, which is an indeterminate. That's why we take help of limits to find limit x tends to c f of x by g of x, and there we can use L'Hopital's rule. L'Hopital's rule says that in one of the cases, if f of x by g of x is going to 0 by 0 at x equals to c, then limit x tends to c f of x by g of x can be found out by using the fact that it is equal to limit x tends to c f dash x by g dash x. Here we present a graphical proof of this statement. Let C1 be a really close point to C. That is, C1 equals to C plus h when h goes to 0. Then we can prove that f of C1 by g of C1 is equals to f dash C1 by g dash C1, which is essentially the same thing as the initial statement. Check this graph. F of x and g of x, where both of them are 0 at x equals to c. Now, if we try to zoom in significantly, such that C and C1 seem somehow farther apart enough, and curves f of x and g of x seem to be a straight line, we can draw two heights f of c1 and g of c1 at point c1. Now from the figure, slope of f of x at c or c1 at any point is equals to height over base. And we know the height is f of c1 and the base is c1 minus c. So that's why the slope of the function at c1 or c is equals to f of c1 by c1 minus c. Similarly, the slope of g of x at c or c1 is equals to g of c1 by c1 minus c. So, the slope of f at c1 by slope of g at c1 is equals to f of c1 by c1 minus c by g of c1 by c1 minus c, which is equal to f of c1 by g of c1 since c1 minus c cancel out, which proves the statement that we made earlier. That's it for today, and guys, 1000 likes for the part 2.